Welcome to the module Real Gases. While the ideal gas law is useful for understanding gases at low densities, real gases behave differently. Today, we will explore these differences and what they reveal about molecular interactions. To understand the nuances of real gases and how they differ from the ideal gas model, we need to dive into interactions between particles. But how do we approach this? At the most fundamental level, we can examine the energy of interaction between just two particles. This figure plots the energy of interaction between two electrically neutral particles as a function of the interparticle distance. This curve represents the Lennard-Jones potential, a common model for intermolecular interactions. It has a simple form with one attraction and one repulsion term. Nevertheless, it offers a realistic depiction of intermolecular interactions. When the particles are spaced widely apart, their interaction energy is approximately zero. In terms of intermolecular interactions, this zero interaction energy just means the absence of interactions. To put it simply, when particles are far apart, they remain unaware of each other, and their energy isn't influenced by mutual interaction. But as we bring these particles closer, the story changes. As the distance decreases, the interaction energy turns negative. Note that negative interaction energy indicates an attraction between the particles. In this intermediate range of distance, the attraction term of the potential is more pronounced than the repulsion term, leading to an overall decrease in potential energy. Then, as particles move even closer, the energy curve reaches its lowest point. This point corresponds to the maximum attraction between the particles. A further decrease of the distance leads to the rise in energy. At first, the energy becomes less negative and the attraction becomes weaker. Then, the energy crosses the threshold of zero and becomes positive. Positive interaction energy means that now there is a repulsion between the particles, as the repulsion term overcomes the attraction. After that, if one pushes particles closer to each other, the repulsion term and the overall energy rise very sharply. It indicates a very strong repulsion between particles, essentially forbidding them to come closer to the range of distances marked by a red rectangle. We can summarize the insights provided by the intermolecular pair potential as follows. When the particles are far apart, there are no significant interactions. The energy is zero. At a moderate distance, attraction dominates. And when particles are very close, they repel each other. As many of you may be aware, from the point of view of quantum mechanics, particles don't possess a definite volume or a radius. Rather, we can talk about how strongly one particle repels another. But for practical purposes, we can assume that this distance from 0 to the intersection of the potential with the x-axis is how close two particles can approach each other. If we additionally consider two particles of the same type, we can conclude that this distance corresponds to twice the radius of one particle. This helps us to figure out at which range of distances the interparticle forces are substantial. The figure also shows that attractive forces dominate within a distance range of 2 to 5 times the particle radius. At distances of 6 and more times the particle radius, the interaction between the particles is negligible. These numbers are of course rough estimates, which nevertheless should provide you with a framework for understanding particle interactions. And so that was the tale of two particles. The interparticle interactions and the energy associated with them are the main causes of why real gases deviate from ideal behavior. As we move forward, we will see how these microscopic concepts translate into observable phenomena. The compression factor Z plays a crucial role in understanding the deviations of real gases from ideal behavior. It is defined as the ratio of the molar volume of a real gas to the molar volume of an ideal gas at the same temperature and pressure. The molar volume of an ideal gas is represented as RT over P, so an alternative expression to Z is P times molar volume over RT. For an ideal gas, Z always equals 1, irrespective of the conditions. Hence, any deviation of Z from 1 is indicative of a departure from ideal behavior. How does the compression factor depend on the gas pressure? If the pressure is sufficiently low, any real gas behaves like the ideal gas. This pressure threshold depends on the temperature and the specific gas in question, but the nearly ideal behavior is achievable for any real gas. It is indicated by the values of the compression factor Z being approximately equal to 1. Depending on the temperature and the specific gas, the compression factor may drop below 1 at certain intermediate pressures. This reduction in molar volume compared to that of an ideal gas arises due to the prevalence of attractive forces at intermediate interparticle distances. When the pressure is sufficiently high, all real gases exhibit Z values greater than 1. It means that they occupy larger molar volumes than an ideal gas. This is due to the domination of repulsive forces. They come into play when molecules are so much compressed at high pressures that they nearly come into contact. As a part of the introduction of real gases, we will briefly discuss the van der Waals equation. The first equation of state that was applied to real gases was derived by Johannes Diderik van der Waals in 1873. In 1910, he was awarded the Nobel Prize in Physics for his work on the equation of state for gases and liquids. The van der Waals equation marked a significant scientific advancement. Accounting for molecular size and intermolecular attraction, it provided a simple and almost quantitative description of many properties of real gases. The van der Waals equation is especially notable for its ability to describe real gases under conditions where they deviate significantly from ideal behavior, such as close to their liquefaction points. Moreover, during the period when van der Waals introduced his equation, the very existence of molecules was still a topic of debate among scientists. Although the concept of molecules had been proposed, their definite existence and nature hadn't been conclusively proven. The success and empirical validity of the van der Waals equation, which accounted for molecular size and intermolecular attractions, served as compelling evidence supporting the molecular theory. Specifically, the equation allowed for the derivation of the own volume of gas molecules. It provided indirect evidence for the physical existence of molecules and solidified the acceptance of the molecular theory. The van der Waals equation represents a remarkable example of model building. In this approach, an understanding of molecular interactions and their effects on the gas pressure guides the mathematical formulation of an equation of state. Let us now examine it. The van der Waals equation in a version shown here explicitly incorporates the total number of moles n. We will focus on the state of the real gas independent of specific amounts and formulate the van der Waals equation using only intensive variables pressure, temperature, and molar volume. Mathematically, we can achieve it by dividing both parts of equation 3 by n. The result is shown on the right as equation 4. In these equations, there are two terms that clearly show their difference from the ideal gas law. Indeed, if we remove them, we obtain the ideal gas law. These terms capture two critical deviations of real gases from ideal behavior. The first term, A over Vm square, corrects for the attractive interactions between gas molecules. The pressure that a gas exerts on its container arises from the collision of its molecules with the container walls. The magnitude of the pressure is proportional to the frequency of these collisions, describing how often the molecules collide with walls, and to the force of the collision, describing how strong the molecules hit the wall. A molecule that is located inside the container is surrounded by other molecules that move randomly. Therefore, the attractive forces from all directions average to zero. However, the molecules that are located next to the container walls are not surrounded by other molecules from all directions. They experience net attractive forces only from the side of the bulk and are being pulled inwards. As a result, both the frequency and the force of collisions decrease by a factor that is proportional to the density of molecules in the gas and inversely proportional to the molar volume. The decrease of pressure is proportional to their product and is inversely proportional to the square of the molecular volume. This is taken into account here. The pressure of a real gas plus the term A over Vm square is equal to what otherwise would be the pressure of an ideal gas. The other term, labeled as B in the equation, accounts for the effective own volume of the gas. When visualizing gas molecules, it's essential to recognize that they aren't mere points in space. As we have discussed earlier, two particles cannot approach each other beyond a specific limit. Hence, imagining them as tiny, impenetrable spheres gives us a more accurate representation. This parameter B gives an estimate of the molar volume occupied by the gas molecules themselves. As a result, instead of occupying the entire volume Vm, the effective volume available for their movement is reduced to Vm minus B. We will now rearrange the van der Waals equation to express the pressure as a function of other state variables. Here you can recognize the two terms that account for attractive and repulsive interactions between gas molecules. In comparison with the ideal gas law, the term RT over Vm minus B increases the pressure, taking into account the actual volume that gas molecules occupy when factoring in their own volume. Conversely, the term minus A over Vm square reduces the pressure, accounting for the attractive interactions between the gas molecules. The parameters denoted as A and B in the equation are van der Waals coefficients. For each gas, these parameters differ and need to be determined experimentally. They are taken to be independent of the temperature. In principle, A represents the strength of the attractive interactions between gas molecules. The greater the value of A, the stronger the attractive forces between the molecules. This coefficient comes into play in processes such as the condensation of gases and might explain why some gases condense more easily than others. On the other hand, B correlates with what we would call the size of the gas molecules. Even though A and B are not precisely defined at the molecular level, they correlate strongly with physical properties that reflect the strengths of the intermolecular interactions. That includes, for instance, the critical temperature, vapor pressure, and enthalpy of vaporization of a gas. Therefore, these coefficients might serve as indicators of intermolecular interactions that affect the behavior of real gases. We can also express molar volume in terms of all other parameters from the van der Waals equation. In doing so, we obtain a cubic equation with molar volume as the unknown, as displayed on the slide. Solving such equations can be quite challenging. A cubic equation can possess 1, 2, or 3 solutions. This implies that for a particular set of parameters, there might be 1, 2, or 3 values of molar volume corresponding to that set. It's worth noting that while closed expressions for the roots of a cubic equation do exist, they are typically quite complex. Unless there is a strong requirement for analytic solutions, we typically use mathematical software to solve them numerically. Graphing calculators can also prove useful, especially in pinpointing which root or roots have physical significance or are acceptable within a specific context.